We're going to wind down the gas law section with two more laws. They will not be before and after type laws. We're going to start off with Dalton's law, and we're going to take a look at this illustration, and then we'll go ahead and look at the calculation. If you take a look at this picture, you will notice that there are 1, 2, 3 canisters of gas, and they each have their own pressure according to how many gas molecules are in that container. Now if I take all 3 of those gases and move them into one container, you will notice that the pressure is actually the sum of all the individual gases. So that's Dalton's law. The equation is PT is equal to P1 plus P2 plus P3 and so forth. The PT stands for total pressure of the gaseous mixture. And the P1, P2, and so forth are the partial pressures of the individual gases. Every gas exerts its own pressure, whether it's by itself or if put into a mixture. That partial pressure always stays the same because it's based on the number of particles of that particular gas. So let's take a look at the example to the left. There are 5 separate bottles, and these bottles represent the different gases that are found in the mixture of air. You can see that oxygen has a partial pressure of 20.9 kPa, and nitrogen is 78.1 kPa, and so forth. You'll notice that when we combine all of those gases into just one bottle, we get a value of 101.3. Now how did that happen? Well, if you just add all of the individual pressures of the gases within that mixture, the partial pressures, you will get the total pressure, which is 101.3 kPa. Let's take a look at the example at the bottom. We had a gas mixture that was made up of oxygen and nitrogen gas, and I wanted to know what the total pressure was. All we would do is just add those two together. 2.3 plus 1.7 gives us 4.0 atmospheres. We also have a modified Dalton's law. If you take a look at the picture to the right, you will see a very common practice when collecting a gas. We collect a gas over water, and you can see in this equation right here that we've got KClO3 that's decomposing to produce potassium chloride and oxygen gas. And so up here in the reaction test tube, oxygen gas is being produced. You can see that the MnO2 is acting as a catalyst because it's not in the chemical equation. And as that oxygen gas moves through the tube and up through the water, it displaces the water and it will fill up the container. Unfortunately, we will also have some water vapor also fill up that container. As that gas is moving through the water, we will get small amounts of water vapor. So when we actually measure this pressure right here, it is actually a mixture of water vapor pressure and the gas that we want, which is oxygen. So in a situation like this, we would actually have to separate out the partial pressure of water from the total pressure of the mixture in order to get the pressure of the pure gas, or what we call the dry gas. So we would have to somehow get the total pressure of this mixture, and that would be your PT. And then you can actually use a chart, and sometimes they'll just give it to you in the problem, to come up with the water vapor pressure for water. Remember that that is based on temperature, and we actually looked at a graph that showed us as temperature increases, water vapor pressure will also increase as well. And so once you have those two, you can subtract them, and that will end up giving you the partial pressure of the dry gas, in this case oxygen. So in this example, I'm asking what the pressure of the water vapor would be if the total pressure of the flask is 17.5 atmospheres and the pressure of oxygen gas is 16.1 atmospheres. So notice that this equation is very similar to what we had said before. PT is equal to P1 plus P2. We're just designating P1 as the gas that we're collecting and P2 as the water vapor. And in this case right here, they've given us 17.5, which is our total pressure, and they've given us the pressure of the oxygen gas, which is 16.1. So it makes sense that we have to subtract 16.1 from 17.5 to get water vapor's pressure of 1.4 atmospheres. The last of our equations is called the ideal gas law equation, and I like to call it an at-now equation. It's not one where we're going to be comparing before and after variables. And it's also one of the first ones that we see where both pressure, volume, moles, and temperature are all combined, and we'll be solving for a missing piece. Now you'll notice in this equation, PV equals nRT, which is the ideal gas law equation, there is an R value. And that R value is new for us, and that is actually called a gas law constant. Now the gas law constant has different values to it depending on the different units that you use for pressure. And so you can see at the middle that there is 3 different possibilities of R, and the most common one that you're going to use is the 0.0821 atmospheres, liters, moles, Kelvin. Now how did these values come about? Well, if we were to take this equation and solve for R, which means we're going to divide both sides by NT, and then we go ahead and we substitute in the standard values for pressure, volume, moles, and temperature, you will actually get these values right here. Every time our pressure unit is different, it actually produces a different number down here. Let me give you an example. If we were to use millimeters of mercury, pressure would be 760. Our volume is going to be 22.4. R is going to be, not R, N is going to be 1, and our temperature is going to be 273. So if I take 760 times 22.4 and divide that by 273, I will end up getting 62.4. The units I used were liters, millimeters of mercury, moles, and Kelvin. If I pick kilopascals, then I'm going to use the pressure of 101.3. I'm still going to multiply that by 22.4 liters in volume, and I'm going to divide that by 1 and 273, all standard conditions, and that'll give me 8.31. But remember what I said a few seconds ago, that this is the most common unit, and if you're ever given a pressure unit that is not atmospheres, you could always convert it to atmospheres first and then use this particular value right here, or you can just memorize these other values and then use them in place of the R. So let's see what a problem like this looks like. A sample with 0.55 moles of gas is at 105.7 kPa and 27 degrees Celsius. What volume does it occupy? Notice they give you moles, which is N. They give you 105.7 kPa, which is pressure, 27 degrees Celsius, which is temperature. They're asking you for volume. So we've hit all of these pieces right here, and this is a constant. So this is obviously the right equation to use. Once we take these numbers and we transfer them into our table, we can plug them into the equation, PV equals nRT. Now the R value is one that we need to think about. Because our pressure is in kilopascals, we are going to use the R value of 8.31 liters dot kPa per moles dot Kelvin. Now if you wanted to use the 0.0821 liters atmospheres moles Kelvin, that would mean that our pressure would have to be in atmospheres as well, which means I would need to divide this by 101.3 kPa in order to put it into atmospheres. Either way will work to get you the answer of 13 liters. Remember that you're solving for volume, so just kind of use your algebraic skills to get that answer. And you'll notice that the answer is in 2 sig figs, and that's because the least number of digits in the problem is also 2 sig figs. Alright, this is our last problem. It's also an ideal gas law problem. This one says, what mass of hydrogen gas in grams is contained in a 10-liter tank at 27 degrees Celsius and 3.5 atmospheres of pressure? So if we take a look at this in detail, I'm asking you for mass. I've given you volume, temperature, and pressure. And so obviously I'm going to use PV equals nRT because I do know my R value, and that would allow me to solve for N. Now N is not M. Remember, N stands for moles and M stands for mass. But we've learned in Unit 3 that moles and mass are related by molar mass. And so the first thing we'll do is transfer all this information into our table. We will use the PV equals nRT equation, and we will solve for N. Remember that the R value has to have the pressure units matching, and since 3.5 atmospheres was the pressure unit, you'll notice I'm using 0.0821 liters, atmospheres, moles, Kelvin as the R value. And when I get my answer, I get 1.42 moles. Now our answer has to be in mass, and so what I will do is I will do a quick dimensional analysis conversion. I'm going to get rid of moles by placing on the bottom. I'm going to put grams on top, and I know that 1 mole of a substance is equal to the molar mass of that substance. Since hydrogen gas is H2, that has a molar mass of 2.02 grams per mole. And so I'm going to put 2.2 on top, and that's equal to 1 mole on bottom. I'm going to cross out my units, and I'm going to multiply the top to get my final answer of 2.87 grams. All right, this concludes the last section in Unit 3. There was a lot of math in this section, but as always, we will do lots and lots of practice in class, and just make sure that you're working through these problems with me and that you're asking questions the next day. Have a great one.